Hello everyone. We are going to discuss the Matlab coding for Fresnel and the Fraunhofer diffractions. The contents are here. The Fresnel and Fraunhofer diffraction allows diffraction pattern calculation, and it's going to be we are going to have a simple Matlab coding, and then we are going to apply that coding to both Fresnel and Fraunhofer approximations. And we do know that the Fraunhofer diffraction is nothing but a Fourier transform. And then we have talked about the Matlab coding for Fourier transformation. But today we are going to talk about the Fresnel diffraction coding, and then we can fully understand how the near field, which is the Fresnel diffraction, is going to converge into Fraunhofer diffractions in this class. Okay, similar to what we have learned in the previous class, we are going to have this coordinate C and eta for aperture coordinate and x and y for our observation point. So basically what we are trying to do is that for the scalar field at the aperture plane, we would like to know the scalar field at the observation point, P0. And mathematically, this equation 4-14 is what we know as Fresnel diffraction approximations. So note that you could see eta is that the scalar field at the aperture field. And then we have this quadratic phase. And then we are going to integrate over c eta plane. And then after integration, c and eta is all gone. And then we have only function over x and y. And then that is the scalar field at our observation point P0, whose coordinate is in x and y. Okay. And actually, you have seen that as a kind of a convolution. So you can see that you could see eta, and then there is a function that has function over x minus c and y minus eta, and then we call it is a point spread function. Okay, so but we are going to focus on this integral, and then how we are going to have a Matlab coding for this expression. So we know that in the region of Fraunhofer diffraction in the far field, we have this further approximation, and then we end up with some kind of phase vector with the 1 over z term. Z is the actual distance between the aperture plane and the observation plane. And then we have a u cos eta, and then we have this exponential term, and then this is nothing but Fourier transformation on cos eta plane to get the uxy. Okay. So basically, we have Fresnel diffraction equations and Fraunhofer diffraction equation. And previous classes, we have learned about Fourier transform here. This is nothing but the Fourier transform. And we have this quadratic phase. Basically, we have three options we can choose. One is the utilize this quadratic phase. And then we are going to look at later on that it is nothing but Fresnel cosine, and Fresnel sine. And another thing is that we are going to utilize the convolution. of two functions. One is this given scalar field at the aperture plane, and this is our point spread function. Okay, and then we have a so-called conv in Matlab, and then we can have direct calculation. And thirdly, we can look at it as a kind of a Fourier transform of these functions. Either way is fine, but we are going to start with this one. So two examples are going to be given. We are going to start with the one-dimensional slit. One-dimensional slit. For instance, you're going to have a slit, infinite slit, in fact. To W, the horizontal axis, and try to find out what is going to come out. And then obviously what we are going to do is that we are going to have a square aperture. Okay. Okay, so now let's start with some of the integrations. Before that, I'm going to change a little bit of the variables. Here we have a U1 and U2 because in the programming, if this U are the same as in the case of here and there, then the programming would be a little bit hectic. So we are going to set U1 and U2 as a kind of a different function, such that U1 is a scalar field at the aperture, and U2, I'm sorry, U2 is a scalar field at the observation point. I'm sorry, this is wrong. U2x. So this is wrong. Okay, sorry for that. So I will correct it in the revised PowerPoint. But anyhow, alpha is a kind of a coordinate in the aperture plane, and the U1 alpha is that scalar field at the aperture plane. And then Q is our quadratic. Q is a quadratic phase here. So as you can see here, this is the quadratic phase. But what we are going to do is that we have two parameter. One is the x dependence, and then it is given as another external parameter, which is the 1 over lambda times 1 over z12. Z12 is that the distance between the two planes. Okay, so it's the observation plane and the aperture plane. And then we further change the variables, and we arrange this one, and then we get the U2 is given by, we take out x and the 1 over lambda z12 out of this integral, and then we have these terms, okay? And then utilizing normalized Fulfil condition, we can write the diffraction equation as, if everything is normalized, then we have U2 is given by U1 times Q alpha minus X as a function of external parameter, Fresnel number, NF. NF is given by these equations, where the W square is the dimension of the aperture, and then we have a lambda and the Z12 here. Okay, so and the U2 is given by, once again, in the same way, we can take out x out of this integral, and then we have only function of alpha. And the b is another parameter which is related with this one. Okay. So we have a very well-defined quadratic phase function over x, and then integral given by this one. Okay, and then we are going to start with the one-dimensional slit. So we are going to assume that u1x is given by rectangular function x over 2w, which means one-dimensional slit with the width over 2w, and such that it is if you look at it, the x is here, so that the origin is at the center of the slit. Origin is at the center of slit, the w above, w down, and then we have this kind of a slit. So origin, horizontal axis. Okay, if that's the case, we note that by the definition of the rectangular function, within this aperture, it is signed as 1, but outside the aperture, then it is everything is 0, so that the integral is confined only to minus w to w. Okay, and then if we further change the variables like t, and then we change the limit over integral t2 and t1, and then it becomes this integral. Okay, and this integral is known as a Fresnel integral. Okay, and then this is our starting point. Fresnel integral has been well known for more than a couple of centuries, and then we are going to utilize some of the numerical values, and then we have written down the Fresnel integral, actually Fresnel x, in Matlab coding, and then we call it Fresnel. Okay, so but basically, if we accept this is the Fresnel function, then what we have here is that minus t1 to 0 minus t. For the case of a t2, it's okay. We can change this integral into two parts, t2 0 something dt plus minus t1 to 0 something dt. And then in order to have a consistency for the Fresnel x, to have this form, we change the variables, okay, and then we change the limits, and then this becomes this one. Here, t becomes minus t, so actually it is t prime, okay, and then because of a minus sign, we get a minus, okay, and because of a minus sign, minus t1 becomes t1, and then by minus sign, we can invert this integral, so we get the t1 up and the 0 down, and then we have this thing. So basically what we can say is that this is the 2 integral, and obviously this part is for t2 w minus x, and this part is the t1 becomes this one, so that w plus x. So we have a 2 term Fresnel integral in terms of a w minus x, Fresnel integral w plus x. And then once we know how to calculate this one, then everything is solved. So we know function of x, which is the scalar field at our observation point. And then we know how it is given. Okay. Okay, I think that to make it short, this is the alpha. So horizontal plane, right? And then we'd like to see function over x, how it's going to spread out. Okay. And here, Fresnel is further breakdown into two terms. Okay, I missed the I here. Okay, c-axis is this Fresnel cosine, and s is the Fresnel sine. Fresnel cosine and Fresnel sine. In fact, we can use actually Fresnel cosine and Fresnel sine. Those two functions are built in the Matlab, so you can just bring out those two functions. And we have a Fresnel coding in our Matlab coding here. So if you unzip the Fourier optics Matlab file, and then we get various apertures, and then we have a slit 2D, slit 3D, and etc. And we are going to utilize Fresnel, and then we are going to utilize slit later on. Okay, and of course we can utilize movie and so on. And there are some other circle shade as a kind of aperture, and some other polygons are shown as a kind of aperture, and you can utilize this one. Okay. So anyhow, what we are going to do is that by defining the Fresnel integral x as this one, and then we know for the slit, one-dimensional slit, then once you know how to evaluate Fresnel functions, then we can find out the scalar field at the observation point. Here, the external parameters are like this. We know that this is the Fresnel number. Okay. And then we have a B is given by lambda z12 over W, which is that basically W over Fresnel number. Okay. And then we note that depending upon the two cases, if Fresnel number is less than equal to 1, then we have this NF minus BX, NF plus BX term comes in, okay, from here. But NF is greater than 1, then the integral is changed such that we get this one, okay, and it is also inverted, okay. So depending upon the Fresnel number, we have two expressions. So it's a good exercise for you to find out how this is done. But anyway, basically we are based upon Fresnel integral, and then depending upon, remember that it has something to do with this one, especially inside this. If inside is that positive or negative, and then we should change the arguments. Okay. Okay, here is the one example. For the case of A, in this case is A is the Fresnel number. Fresnel number. And as you know, the line space is that the linear space divided from -2 to 2, -2 to 2, and then it has a 800 segment, okay? And then Fresnel routine in the Matlab coding I have provided you. For the given argument, it assigns you the cosine and the sine value here. And for this, we have a cosine 1 and a sine 1. Okay. And then what we are going to do is that Z is given by, is the scalar field. And then it is given by complex cosine term is all added up, and sine terms are all added up. Basically, it's a cosine something plus I something. Okay, this is our I sine something. Okay, so this is our Fourier integral. Remember that the Fresnel integral. Fresnel integral is actually the complex number, and then what we have to do is that we get the Z times conjugate of Z. That will give you the intensity. So this is the Z. Z is U2 and F is U2 squared. Okay, and then we further normalized it with this value. But you don't have to actually. You don't have to do that. But in this case, I just used the normalization. Here we get this kind of functions like this. Okay, for Fresnel number over 0.5. Okay, so it's a kind of a you can see that we know that the aperture rectangular function, if you do the Fourier transform, then you get the sinc function. So it's just sine x over x. It's getting close to sine x over x, but it has something here. It should go down to 0, but anyway, it is in between. Okay, so it is kind of a far field. So what about the NF equal 2? Remember that the NF equal 1 is the criteria which flip the expressions. Okay, this is for the near field, and this is this is for far field, and this is for the near field. Okay, so as our example, first example, NF equal to 0.5 has been shown, and then NF equal 2 definitely larger than 1, and then we get the same thing. It's the same routine for the Fresnel CC2 and SS2, CC1, SS1, we get this one. One is the certain value minus x, certain value plus x. And then we get z equal to is here the complex conjugate here is this one. This is U2 squared. Okay. And then we plotted the U2 square. Here is the f, actually plot f. Okay. So now you can see that it is a little bit strange looking pictures are shown. Okay. And then what we are going to do is that we are going to come up with another function which is called slit. Okay. And slit A will give you function over f and x, function over fx. Okay, that is a kind of diffraction pattern. So slit requires A. A is same as before, is a Fresnel number. A is a Fresnel number. And then it is using same Fresnel routine Matlab coding, and then it calls Fresnel here. So if the Fresnel number is less than 1 or else, that means A is something, and then we get this value and this value here, and then we get this one. This is the U2, and then F is square. Okay. If A is less than 1, then we have to normalize it with this factor, and then plot function over f as a function of x, and then we have this k with different options for the plot. Okay, so here is the case. We have 3 plots: nf equal 10, nf equal to 100, and nf equal to 1000. So remember that nf, the Fresnel number, is inversely proportional to z. That means if nf is large, that means the z12 gets smaller and smaller. So that large Fresnel number, like some 1000, its diffraction pattern looks like a kind of a slit itself. Okay, slit itself. And then as z increases, and then nf gets smaller and smaller, and then we get these Fresnel diffractions. Okay, and then we get this one. So if we reach nf equal to 1, then we are getting into far field. We are getting into far field. Okay. And then if we reach a smaller, even smaller number, 10 to the minus 8, 0.05, 0.25, and if you look at it, it's all the same, But remember that the intensity will go down as z increases. Okay, and then as you can see, it is basically it's a far field, and it is indeed is a sine x over x, which is a single function, which is the Fourier transformation of the rectangular function. So what we now here see is that using this Fresnel integral, Fresnel routine, then we can cover near field and far field in every possible Fresnel numbers. So we know how the field will evolve from near field and then far field. Okay. This is great. So that what we now know is that Fresnel integral will converge into Fraunhofer integral. There is no discontinuity. In fact, there is no discontinuity between the Fresnel diffraction and the Fraunhofer diffraction. Even though its pattern is totally different, the Fresnel integral will have a converging value to the Fraunhofer diffraction, which is nothing but the Fourier transform. Okay, this is the beauty of the diffraction. So now let us try to think about Fresnel diffraction by a square aperture. The previous case we have thought about the one-dimensional slit. Okay, and then we are going to talk about a two-dimensional square aperture. here. So square aperture with the width of 2W, then we have this horizontally 2W and vertically 2W, and then convolution form of the Fresnel diffraction is given by this one. Okay. For both C and eta, it's going to be minus W to W, minus W to W for this quadratic phase term. For x minus psi square and y minus eta square. And then substituting what we have learned in the classroom, then our field at our observation point is going to change into Fresnel cosine, Fresnel sine, Fresnel cosine, Fresnel sine for different limits. Okay, and then intensity of the wave field is given by the absolute square of this value, such that we get 1/4. This comes, and then we have these terms. And then what we now know here is that once we know how to calculate the Fresnel cosine and Fresnel sine, then everything is done. Okay. Here the limit is alpha 1, alpha 2, beta 1, beta 2. Here is the alpha 1, alpha 2, beta 1, beta 2 is given. Okay, for different values here. Okay, so if you look at the entry of the free optics Matlab file, G file, and then there is a slit 2D, and then slit 2D, when you open it in your Matlab editor, and you will see this one. Okay, so it has 800 points, and then we have X and Y. Okay, and it starts from the -1 to 1, -1 to 1. And then we have a Fresnel cosine Fresnel cosine, and the Fresnel sine is obtained from the Fresnel routine. Okay, and then we have this value for Fresnel number is less than 1, we get this one. If the Fresnel number is larger than 1, we have this one. And then we get the diffractive field on the x function of x and y, and then we get the intensity. Okay, and then we can get the plot for this one. So here is the case, far field diffraction case. Here, sorry, this is the Fresnel number is 10, and Fresnel number is 0.5. And 0.9, and here is the NF1. NF is 1, NF is 8, 1600, okay, and even thousands, 10,000s, okay. So in the case of a far field, we know that it's going to be sinc function on both x and y axis, okay. And then we did not know how it would look like for the very near case. The field at the observation field, it should very similar to the aperture itself. And then as it move away, and it shows this kind of ripples, and then eventually it goes down to the sinc functions. Okay. And in order to do that, we have these movie files, and then we get the frame, and then we close these frames. It has 1,000 frames, and then we change the pictures into the movies. Okay, now let's see how it goes. As NF is decreasing, it shows how the field would evolve. So you can see that those ripples, and then it looks kind of a random, but it is not. It is all mathematically predictable. It is predictable. That is the beauty of Fresnel diffractions. Even though it looks very random, but eventually we can actually predict Fresnel diffractions. And then it's getting there. You see those functions in this y-axis is nothing but what we have seen before in the one-dimensional slit, and then it goes. Okay, remember that in the far field, okay, this is the sinc functions, and then sinc function stays, but the amplitude will decrease. Okay. Okay, so what we have done today's lecture is that we have utilized the Fresnel metal coding that is given to you, and then the Fresnel cosine and sine. So Fresnel MATLAB code will give you Fresnel cosine value and the Fresnel sine value. And then once we know Fresnel cosine and sine, and then we can evaluate the field and the intensity at the observation point. So what we have seen here is that we have actually seen near field to far field evolution for one-dimensional slit and then two-dimensional aperture. Okay, so we have seen that how the slit is going to change, how the aperture is going to change. Okay, so we can do the simulations using actually convolution and angular spectrum method, and I think that it's going to be a very good exercise for you. Try to utilize these conv functions. And angular spectrum is you start right away from the Fourier transformations, and then we can do the very similar stuff. Okay. So today what we have learned about is that utilized in Fresnel routine that I give to you, we can actually simulate near field to far field evolution. Okay, and this could be applied to any type of aperture. So we are going to think about other cases in the coming classes. Okay, thank you.